So today we're going to do lectures 7, 8, and 9 that are all related to input and interaction and callback events. So let me see if I can figure out how to start my presentation. Here we go. So this first one is lecture 7. If you download the PPTs, you can get all the information on this. And what I'm going to do today is go through a bunch of input and interaction stuff, and then next week we'll see it live with some examples, and then I'll go through some other stuff. But it's, I actually kind of have to explain the concepts to you and the vocabulary that's associated with it, but and then we'll see it operating in OpenGL. But input and interaction, kind of fun, kind of basic. This is where we get our event-driven behavior and our event-driven programming. So the objective of this particular lecture is to introduce the basic concept of input devices that applies towards all computer graphics, not just OpenGL. Looking at the physical devices, logical devices, input modes. So this is where you're going to get your vocabulary from, or your basic computer graphic concepts. We're mostly familiar with event-driven input already and event-driven programs from other types of programming environments such as Java, Visual Basic, C++, where we have a GUI and the GUI shows up on the screen, and when we click on the GUI we have an event that occurs, and then we have some sort of a procedure, function, module, or something that's programmed to react to that particular behavior. And that event-driven program is identical in concept when we apply it to computer graphics. The only thing that we have with computer graphics that we don't actually have with other types of application development is that the event-driven can be from inside of the program too. As an example, if you have, let's say for example, you put up a bunch of dominoes and the user knocked one domino, well that's probably going to trigger an event. You know how the dominoes all fall down and they're all stacked up. You're going to have events driven, or events that are created from one object hitting another object perhaps, or you're going to have, let's say for example, some animation that you don't normally have in a regular old event-driven program. So rarely are you in an accounting program and the mouse is moving on the screen, or you have some avatar come out and do something, which you're going to have in a graphics type program. Because if you think about it, most of the graphics applications these days are games, or they are interactive type programs or fantasy programs, and it's kind of different type of programming where event-driven behavior is very popular. So I'm also going to introduce the concept of double buffering for smooth animations. In fact, the buffering for the event-driven behavior is a lot different. Because if you think of the concept of that, going back to that accounting program, when you click on a button to input a debit or credit or something like that, it's data. You know, it's a piece of text. It's coming from a form, and the input's going to submit it. It's going to maybe do a query or something. It isn't going to render an image on the screen or move an image or calculate something that's going through the graphic buffer. So in terms of the buffering, in order to get that smooth stuff, you must have to premeditate ahead of time what's going to happen and have already pre-clipped images and pre-buffered stuff so that it can show seamlessly without any type of jerkiness or something. And then look at the programming events input from the GLUT utility. So in terms of the project, in terms of project Sketchpad, where this all comes from, and that's one of the interesting things about OpenGL is APIs. It's kind of written by a lot of different people, and some people have contributed. It's open source, so a lot of people have contributed to it over the years. And today's version of it is nothing like it was back in 1963. Because 1963 established, this particular guy, Ivan, established the basic the interactive paradigm that characterizes the interactive computer graphics. And so what he kind of developed, and this is implemented in the OpenGL, so the user sees an object on the display. The user points to or picks the object with the input device. May there be a light pen, a mouse, or trackball. And there's actually a new OpenGL Touch library interface actually that's in beta right now as well. So consider your new touch screens. And let's say you're using OpenGL as a utility in an iPhone application or something like that, or an iPad application. All the event-driven behaviors, believe it or not, is the same. It's all processed the same way. We just have different calls, essentially, that are going to take the input from different sources. So we have an input source, we have an output source, we also have the object changing, as I mentioned before, moving, rotating, morphing. And then we have repeating that goes on. So it's a little bit different going back to the comparison between regular old GUI programming with a Windows application and a graphic event-driven behavior. The event-driven stuff for the graphic is definitely a lot more entailed, a lot more complicated in terms of the abstraction of what's going on. So let's talk about input devices. Those are the easy ones. We all know about physical properties. We've got a mouse, a keyboard, a trackball. We have left button, right button, pointing, clicking, double clicking, single clicking, all of the different activities that might occur. In terms of touch screen, that comes a little bit more complicated in terms of the gestures that can be done on a touchpad with hands and fingers and things. Logical properties are going to be what's returned to the program via the API, what's being captured. So we have the physical properties, which are going to be the actual buttons, the actual input device. The logical properties, that's going to be the position that's oriented on the plane or in the XYZ coordinates. Or maybe perhaps the object, what object was clicked on. That may also be an important component to be considered. And looking for my watch, here we go. So also the modes, how and when the input is actually going to be obtained, and the request or the event that might actually occur. So in terms of the modes themselves, that's basically going to create our interactivity. In a Windows application, as I mentioned before, the mode is basically load up, sit there, and wait. I mean, when you load up an application on your computer and you're waiting for it, the program is actually waiting for your user input. You're going to click on something, you're going to select something, you're going to open up a new file or something. In a graphics mode, it may not necessarily be waiting for the user. It might be waiting for an event to occur, or might be waiting for some input or some sensing of something. Somebody touched something or something. So the request for the event is kind of interesting as a side comment. In terms of the physical devices, those all should look pretty familiar to you. Don't worry about it if you don't know what. Actually, do we still have joysticks on the market? I think we do for game playing. Well, now with everything in terms of Kinects and the Wii and stuff like that, we're going to add those devices here too. But the input devices, the physical devices, are fairly straightforward because as a consumer you've used them a lot. So, in terms of the relative devices and incremental relative devices, devices such as data tablets return a position, usually, directing it to the operating system. Usually there's a pass-through, and we actually get this the same way with Windows, actually. And any graphic user interface, there's a pass-through to the underlying operating system. It's sort of like how we would generate a signal or an interrupt that would say, hey, the user pressed Control-C, which would be treated differently than the user clicked on the mouse. So that's essentially the incremental in terms of the device themselves. We have a whole list or a stack of these things that can be sent. So as an example, if you're playing with the mouse, you're going to have, let's say, I don't know, the opportunity to move the mouse all over the place, opportunity to click all these buttons, you can click the keyboard at the same time. All these events are queued up, actually, and they're handled one at a time. If they weren't queued up, we would have to have a real-time sort of reactive system, and some of the events were currently being processed, and we might actually miss another event that shows up, or something else might happen. So there's an entire scheme that's played, or that's orchestrated, let's say, to capture the events, queue them, send them to the underlying operating system so that they can be dealt with either from a kernel level or from a user mode. So the data, so as a data tablet, so it's returned to position, let's say the device such as a mouse, a trackball, a joystick, might return an incremental input or something to the operating system in terms of its properties. Must integrate these inputs to obtain an absolute position. As an example, the rotation of a cylinder in a mouse, rolling of a trackball. Difficult to obtain absolute position sometimes. You can also get a variable sensitivity. And this is where game playing actually makes for some really bad experiences or some really good user experiences. How reactive is the graphic to your command, to your input? As an example, if you're playing a game and you are shooting somebody, and when you press the gun control, the bullet took 2 more seconds to come out. Or, you know, that would be as bad as watching a movie when the sound doesn't match the lips that are moving. Everything's out of sync. So that's an important property to consider in terms of the graphic application. Graphics is going to take a lot longer to render than the input. So having the user experience actually synced so that you press a mouse, you move something, and it correlates instantly with some sort of a graphic change from the event that's occurred, which gives us our realism. So when we have the input, and the input is captured by the application development environment, the API picks it up, we can consider as an example what happens if we're writing a C or C++ code, or let's just say C++. We're all familiar, if you've done some C, hopefully you have, because you're programming in C in this course. So if you've done some C, we've got the scanf, we got the printf, we got the cin, we got the cout, in terms of I/O commands from iostream.h and stdio. And those are basic libraries that define the input-output. In a C, C++ program, we're primarily looking at keyboard. And we're primarily looking, if we're doing an MFC application, we're looking at a Windows interface motif. We're looking at mouse events too, and we have a separate environment for that. What ends up happening is an event-driven application is created in which there's a wait for an event, so there's an event handler that occurs, and then when the event is caught, then the event is processed and dealt with. So, in terms of the input device, you can't tell from the code what the device actually is. All you can do is get the signal from the underlying operating system. And here's the interesting thing, and which kind of causes a little bit of complexities in terms of learning graphic and in terms of learning event-driven behavior. It's all coming from the underlying operating system. So there's absolutely no way for an OpenGL type of application to actually pick up the event. It's reading it from an operating system call. So it depends on the platform that you're on as to how this is actually going to be programmed. So you could have an event that's triggered from a keyboard, a file, output from another program. Any number of different scenarios might exist in terms of the input. So the code provides logical input as well. So the number and integer is returned to the program regardless of the physical device to say, hey, I caught a mouse or I caught something and I processed that. So you catch it, I'm going to go back into that scenario, catch the event, which is kind of generic terminology. It's kind of like a try-catch in a C++ environment, or in a Java environment, and you are looking for something in particular. When you find it, you're getting a code. It's usually an ASCII representation of an event that has occurred that's been passed to you from the operating system. And then you're creating an event handler to say, well, if the user does that, then rotate the image. If the user does that, then send a bullet out the gun or something. This is the interactive play for a game or something. In terms of the logical, separating the concept from the physical, the logical properties of the events and the information that's coming into the system, we have the graphical input that's varied, so more varied than the input to the standard program, which is usually members, characters, or bits. So we have 2-order APIs that work with this that define 6 types of logical inputs. And here's where I said I'm going to give you some information that's going to be more concept-based for generic computer graphics, because this applies towards everything. Just doesn't, it's not limited to OpenGL or the Galette library. We have what's called the locator, which is a return position, might be the return position of where the click occurred. So instead of comparing this to a Windows library and in a Windows development environment from a programming language perspective, we don't get mouse button clicks. We don't get this was a text box. Clicked in a text box. Clicked into this. Clicked in. Instead, we have to work at it for more on the plane, from the XYZ plane, and figure out how the particular event's going to be handled given the type of input that we're getting. So here we have the locator, we have the pick, which is the return ID of an object that has been clicked on, or that has been, essentially the target for the event. The keyboard is going to return the strings of characters that were pressed. The stroke, returning an array of positions, perhaps. The validator, returning a float number. And, in terms of the choice, returns one of n items. If you had like a couple of choices clicked up and the user clicked on one of the choices. That might be a multiple selection box, maybe some radio buttons or some GUI element. But the interesting thing is we don't really have multiple selection boxes and GUI elements like that in a computer graphics application. Instead we have objects. So if there are 5 different images, we clicked on one of them or we clicked on a portion of the image, that would give us our selected object. So here's our X Windows input if we were to compare it. The X Windows system, this is for Linux, Unix type of environment, introduced the client-server model from the networks of workstations. So the client might be the OpenGL program. And then we have the graphics server, which is going to be the bitmap, maybe displaying with pointing devices and keyboards. And this is kind of a picture of a client-server environment for which we have a file server down here and some graphics servers and workstations that are all connected together. So given the platform, the physical hardware, the logical characteristics of it, we program the environment given the input modes. So the input modes contain a trigger, and the triggers which can be used for sending a signal to the operating system. So you have a joystick or you have some component that's inputting something. They actually do call it a trigger. So a button on a mouse, pressing and release of a key. So when triggered, the input device returns the information, their measure of the system. And so the mouse returns the position information, perhaps the keyboard returns the ASCII code of what was inputted in. And then we have the request mode. So input is provided to the program only when the user triggers the device. So the program just sits there, and then the input comes in on a, event-driven kind of demand. So typical of keyboard input. So unless you're doing something in which you're having some sort of an animation occur, you're essentially, the application's waiting for you, you're going to press a key. The key might be to play a game, an up arrow key, a down arrow key, or something. So you can erase or backspace, edit, correct, until entering the return key. When you hit the return key, the trigger is dispersed. So the OpenGL library actually will save up all of the keys that you're pressing in. When you press and enter, it's going to trigger that the input should be sent to the operating system, and then the input from the operating system is going to then be translated and converted and then sent back to the application program that's running it. So we have the trigger processes. So the process of it, the trigger, the measure process, the measure gets sent to the program, and then the request goes back to the measure process to say the user pressed in help, or the user pressed in the escape key or something. And then we can figure out what was pressed. And then we have the event mode. And the event mode, so most systems have more than one event device, keyboard, mouse, joystick, something, each of which can be triggered at arbitrary times by the user. There's no requirement that the user hit every input device in the same order. Each trigger generates an event whose measure is put in the event queue. As I mentioned before, the event has to be queued up. If we don't queue the events, we're going to lose them. It's kind of like how interrupts are dealt from an operating system kernel perspective, or how the keyboard input is actually buffered. And the buffers actually exist that is nothing more than the contents of a queue, usually in the form of a stack. Because it can capture all of the items, put it into a stack, and then pop each one of the items off and when it processes the various different events with the various different keys that were pressed on the keyboard. So the event queue can be examined by the user program. Here we have the trigger process triggering the measure process triggering the event queue. Event queue says, oh, here's an event, sends it to the program. Event to the user, click the right mouse button. The program takes it back to the event queue after it processes and goes, okay, what's next? What's next? What's next? And here we have this loop that occurs with the events, so that all of the events can be processed out of the queue and everything can be essentially programmed seamlessly. So we have different events types, which is kind of interesting. And nobody memorizes all of the different types and all of the different events and all the different key codes, unless you guys sit home and memorize ASCII key tables, excuse me. It's kind of insane. So in terms of a window, some of the typical, and this is not a complete list, a resize, an expose, an iconify, the mouse, a click of one of the buttons normally, or the tracking of the position. The motion, moving the mouse. The keyboard, pressing and releasing a key, and then no event at all, which would be idle. So define what should be done if no event at all is in the queue, and we have a timer. Actually, there's a timer component we haven't really talked about yet that sets, for example, a storyboard. So we can create some event that's going to occur on no event after 5 minutes or something, which might be the program might be the program shutting down, or a screensaver coming on, or something in the application resets itself or turns itself off, as an example. It would be nice if all appliances just automatically turned themselves off, but they'd have to be looking for an event that said there was no user activity. So kind of like the sleep mode of a computer, I guess. And we're familiar with callbacks because we've seen it so far in our basic application. So programming the interface for the event-driven input may also entail a callback, and actually it will. We define the callback function for each type of event that the graphics system recognizes. So we have our main callback for the application, and then for each one of our different events, we separate it out, create another callback function for that particular handling of that particular event. This is a user-supplied function. It's executed when the event occurs. And here's an example here of the GLUT example of the mouse function. So this is the mouse callback. So mouse callback function, my mouse, is going to be called when we're, basically the event of a mouse activity is being triggered. Here's some more examples to recognize a subset of events recognized by any of the particular Windows systems, Windows, X, Macintosh. And that's one of the actually nice things about OpenGL. It's not cross-platform compatible, but the API works the same. It just gets the events differently for a Windows versus a Mac system. So it might be a display, a mouse, a reshape, a keyboard, an idle. So these are all different functions, the motion function, passive motion function, all the different options that we have in terms of the callback events that we can do. And we actually have been working with an event so far. This is the one we saw with Hello World, the OpenGL program that, first one we looked at is the main loop. So the event loop itself is part of this body of this body of events and event-driven programming. So recall that the last line in main for any program using GLUT must have GLUT main loop. It sets the state machine, the application that you're running. So this puts the program in an infinite loop. And each pass through the infinite loop the functionality to listen to the event. So we don't actually have to implement an event listener like we do in another language. This has already got it in the main loop. So it looks for any events in the queues. For each one of the events in the queue, the GLUT's going to execute the appropriate callback function, which is going to be our catch. If one of these is defined, if it's not defined, it's going to ignore it because it doesn't know what to do with it. So if no callback is defined, the event is ignored. So our display callback. This might look familiar. We've worked with this so far as well. So this is another thing that every program has. So our GLUT display function, myDisplay, identifies functions to be executed. Every GLUT program must have this display callback, otherwise we have no way of displaying any of these items that we've created on the screen. So the display callback is executed whenever GLUT determines that the window should be refreshed. So for example, when you first open up the program, so it's the first open, it needs to paint the screen that you've created. When the window is reshaped, when the window is exposed, when the user determines it wants you to change the display. So this comes in handy if you haven't figured it out already. When you start working with events and you start moving the screen around, you have to call the display function again to go through the loop to redraw the scene at the particular coordinates that you've changed everything to. And the user actually puts this call in here just like you put it in main when you started up the program. So posting the redisplays. Many events may invoke the display callback function. Many events invoke it. Also, the user can explicitly invoke it. It can lead to multiple executions of the display. Single pass through the event loop. So we're calling it multiple times, which could be a problem. So to avoid this problem, we can use instead the GLUT post redisplay, which means if it's already there, just redisplay it. If it's not, if it wasn't just called a few minutes ago, won't do it. Otherwise, what ends up happening is you get a screen that flickers. You get flick, 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 because you're painting the screen, painting the screen, painting the screen, painting the screen. So all these little callbacks are triggering the display function, callback. And so it's kind of, everything's going to go away for a second and come back. So it's not a desirable. So to get around that, there's a built-in post redisplay. And you set the flag for that, and it'll look, and after all of the events have occurred, and after everything's been done, then it'll redisplay. Instead of doing it 10 times, it'll only do it once or something. So that checks to see if the flag is set at the end of the event loop. If it is, then run it. So if it's set, then display callback function is executed. If it's not set, don't execute it. Kind of thing. This is a waste. So animating the display, we've seen actually the GL clear. I showed you that too actually with our hello world. So when we draw the display through the display callback, we usually start by clearing the window, the GL clear, then draw the alternative display. One of the problems might be that drawing of the information in the frame buffer is decoupled when the display, from the display of its contents. So we have a dual ported memory, essentially what we're working with here. So we could have contents on the screen that are not in the buffer. We could have something that's supposed to be happening that doesn't exist, or we could have double or contradictory images that might not display properly in terms of what's in memory, what's buffered, and what should be displayed. So hence, we can simply see partially shown displays. This actually happens a lot. So there's a program, and I put out in the examples directory called single_double.c with a rotating cube that makes a mistake actually. Partly it rotates it, but it doesn't. It rotates it too fast for the display, and the program is actually not set up correctly. There's an issue with it in which part of the cube doesn't actually show at certain points. And it's basically put out there to show you why double buffering is needed. So with a single buffer, as a kind of a small example, if you're making a change and you're storing it, even in any other programming language that you might actually be working with as an example, what we have is a single value that's stored for something. It's like when we keep memory about in variables, and then we update the variable. Well, we could have a loop that's updating a variable that might show the wrong value for somebody else who's using the loop, which, is a classic interprocess communication problem. When we apply it to graphics programming, it's kind of similar, but it's a different problem. It's the buffer's not going to contain what we need it to contain, because the buffer is going to be rewritten. On a single buffer, we can only store so much, and the buffer can change before the image is actually rendered correctly, or before the graphic actually shows up on the screen when we're doing a display on it. So the double buffering came along as a way of pre-storing everything you need, kind of thing. So we can reuse it when we need to reuse it. So instead of one color buffer, we can use two. In this example, we have a front buffer and a back buffer. So one that is displayed but not written to, and one that is written to but not displayed. So program then requests a double buffer in main.c, and we do this by doing double buffer instead of single buffer. And at the end of the display callback, the buffers are swapped. So it's not displayed, so one of them is displayed but not written to, so we're not changing it. The other one is written to but not displayed. And so it helps us keep track of the information a little bit more streamlined, if you want to consider it that way. So here's my drawing a swap. This is a swap buffer of a double buffer. So we keep swapping the buffer to render the image so that we can essentially make it so it's not going to flicker, not going to be half drawn, because we're not going to ever lose information. If we use two separate buffers in unison to render the image onto the screen, we're never going to end up with a cube that's half drawn. If you want to see the effects of what happens when you don't use double buffering, take a look at single buffer. It's going to do something that should really require a double buffer mode, because it's going to render something while it's changing it, and the change is too fast. The buffer actually gets, I don't want to say corrupted, it gets overwritten is what happens, because we're reading and writing to the same buffer. So if we're only reading from one and writing to one, and we're just one is being displayed and the other one the one that's being displayed is not being overwritten simultaneously, then we're sharing it out. We're doing double buffering essentially. So using the idle callback, and this, don't worry about it. You actually just set the parameter for the display mode to double the buffer, and it's built in automatically. It's nothing the programmer actually has to work with. Thing is, this is going to take up a little bit more memory. So if you have a, you're not doing any animation, why double buffer? And so far you probably haven't done any animation yet. So single buffer is just fine, really. It's only when you're doing animation, you're actually changing the image and you're having something happen that you're ever going to have a problem with it being redrawn correctly. So in terms of the idle callback, we can check to see if the system has been idle. We can put a message that says, hey, press a button to start the program. Or, hey, are you still there? Should I shut down? So the idle callback is executed when there is no event that's being occurred. We have the let idle function. So useful for animations. So this is where you get like in a situation where a little paperclip comes out because no one's pressed anything yet, and it goes over and it animates some some menu, or it does something to create an interactive environment for which the user can learn, or signal to the user that they should do something. That actually I find that actually irritating personally. I turn those features off. Because if I'm not using the program, it's because I don't want to use the program. But in other situations, in terms of animation, if nothing's going on, other stuff can go on. Here's a classic example of why it's used a lot in animation. What if you want to, you've repainted the environment, you've redrawn everything, things have been idle for a few minutes. It's kind of like what operating systems do. When you're not using your operating system, there's an idle catch. Idle function, and so let's use this time to clear out the memory, or to clear out buffers that aren't being used, or to do some maintenance on something, because operating systems do a lot of maintenance when you're not aware of it actually. Go through, check, make sure all the running processes are running correctly, and shut down anything else, and do all this other work. Well, graphics programs can do the same thing. So you can automate behavior that happens when the program is idle. If it's like a game program or something, you might just go through and clear out buffers that aren't being used anymore, clean up the memory, I don't know, maybe repaint the screen or something, or do something that's productive when the things are idle. Because what you don't want to do is do everything while the user is trying to use the game. So if stats or something have to be calculated, and there's a little bit of idle time between play, calculate the stats. That's something happening. So we can also use globals. So using globals here, the form of the let callback is fixed. We have, as an example, void my display callback function, and we have my my mouse. That's going to have a button, a state, an x and a y, z coordinate for the mouse. So it must use the globals to pass the information to the callback. So the globals are built in; they're defined for us. We just use them. So we can, as an example, float t might be a global variable that's going to capture, draw something that depends on t. And then we can use t throughout, and what is referred to as global. We use it throughout all of the different functions. So everything is relative in relationship to an x, y, z coordinate or something like that. So we're not done yet. That was the first lecture. That was number 7. And now I'm going to go through number 8. Number 8, and all 3 of these are on the same subject. They're all on event-driven programming and interaction. Number 8 is about 20 slides, and it's going to go through some more of the callbacks and working with designing callbacks. Because what I just gave you is the overview of the event-driven behaviors, the callback concepts, and the different types of functions that can be created. So when working with callbacks, we're going to learn to build interactive programs using the mouse, the keyboard, and Reshape, and introduce the menus. So there's also the menu concept, which is actually kind of easy. So the mouse callback. So the mouse function, as we saw in an example that just ended with in the last lecture, we have glint button, glint state. Say, for example, x and the y, which is going to be the coordinates on the plane for where the mouse is coordinated at. And this returns which button, so we get the left button, the right button, the middle button, cause the events. And believe it or not, we can actually have a mouse that only has 2 buttons, doesn't have a middle button. And the mouse, as long as the hardware, physical hardware is mapped correctly with the driver and the operating system is getting the information correctly, it's generic. So this works with any mouse. The state of the mouse, whether it's up or down in terms of its movement, the position in the window, these are all different things that we can capture in terms of the mouse. Here's our positioning as an example. It's XYZ coordinate. We don't have 3D mouse controls, which is interesting because we take the 2D, the XY coordinate of the mouse position, and then we apply it to a 3D plane. So you can click in a 3D plane with an XYZ, and you can actually get the XY coordinate for it, and it works, essentially. Whereas we're still looking at a flat surface in terms of the mouse capture. So the position in the screen window is usually measured in pixels, and with the origin at the top left corner. So up here would be 0, 0, and then we have, all the way down to the biggest number, essentially, corner to corner. Consequences, a refresh is done from top to down. Actually, you could see it in old graphic hardware. Really, really old graphic cards applied towards, those old monitors. You could actually, if you watched close enough, you could see the screen being painted this way. So it actually starts at the top and it gets painted down this way. Now it's so fast you don't even notice it. In fact, it's the default way of actually painting the screen is to do it from the top to down. So OpenGL uses a world coordinate system with origins at the bottom left. So you must invert the Y coordinate using a callback by the height of the window. So Y is equal to height minus Y. So we can get the coordinate system essentially on the OpenGL world plane and put it into an XY system. So obtaining the window size. So to invert the Y position, then you need a window height. So the height can be changed during the program execution. This would be the size of the window height, making it smaller, making it bigger, resizing the window, tracking with a global variable. New height returns a reshape callback automatically. That will look at the detail. Well, we're going to look at the detail soon, but the reshape callback to resize the events in the window is called automatically on a window change. You can also use a query function to get the integer value, get the float value to obtain the values that is a part of the particular state that we're looking at here. So terminating a program. So in our original programs, there was no way to terminate them through OpenGL. You notice even the hello world, you had to pretty much just close the window. So we can use a simple mouse callback to terminate, to set maybe a close button or something. So we have the button state, the XYZ, and we have a button in a state that we're going to catch in terms of the button. And using the mouse position, so in the next example we're going to draw a square, small square, at the location on the mouse where each time the left mouse button is clicked, it's going to do something. So this example does not use a display callback, but one is required. We actually have to put it in if we use GLUT. So we can use an empty display callback, myDisplay empty, to actually facilitate this. This draws squares at the cursor location. If you've ever seen those irritating programs with those animated cursor icons, I don't know if you're familiar with those, but you move the mouse and you got this trail that follows the mouse, or you have, that's an image that's being painted, or you have like a character, you try to move the mouse towards something and the thing moves. Click here to win $10,000, and every time you move the mouse towards the object goes away. This is how it's done, actually. It's in looking at the coordinates, the XYZ coordinates of the mouse. When you click the mouse, it's going to draw a little square, essentially, at the coordinate system where you put the mouse. This basically is just nothing more than an example to show you how to work with the mouse events. In fact, I believe I have this code cut and pasted and put into a source code example for which you can download and take a look at if you're inclined. The code here is not going to be, as mentioned before, there's the display callbacks not implemented. So the code is kind of very crude, but it's showing you an example of the difficulty of the function calls, which is not that bad. So it's identifying, which button is it and which state is it. If this is the button and this is the state, then exit. So this is putting in, if you click right here on the window, then close the window. So you could put something right here, like a little X or something. And then when you clicked on it, it would close the window, essentially, because it's performing an exit. So, or draw a square if you're pressing these other combos. And then we have the draw square, but draw a square at the X, Y, Z coordinate. I'm just going to draw a square. So it's actually kind of a simple little example. So using the motion callback, you can draw squares or anything else continuously along a mouse button. Mouse button is depressed by using the motion callback. And then we have the glet motion function, draw a square. So you can draw squares without depressing the button using a passive motion callback. Passive motion callback, where you don't press buttons, and so you just move the mouse and it creates that square for you. So in terms of using the keyboard, you might imagine it's kind of simple, except for we have the ASCII codes to pick up. So the glet keyboard function with key that's entered in. So we have, as an example, sample void my key. It's going to have a key character code that's going to come in as an unsigned character, and an X and Y coordinate. So return the ASCII code of the key that's depressed and the mouse location. So you put the mouse over here and you press a key, you can actually capture both simultaneously, the mouse pointer area and where you're typing. So for example, you want to put up a web form or something, you want to put something, an input box. If you clicked in the box, it's going to pick up where the mouse is, and you're going to be able to type in, it's going to put whatever you're typing, let's say, in the box or something. It's primitive. If you were going to do this, you might as well just use C or C++ or some web form, HTML. So, special and modified keys. So the glet defines a special key, glet.h, seen before. Function keys, and these would be function keys as an example. They still put them on keyboards too. It says FN or it says function, and they're usually at the top of the keyboard, like for example F1, F2. The up arrow keys, the down arrow keys. The reason why there's so much support for this is that a lot of the game programs use the function keys or they use the arrows to navigate the game in terms of the input. Use the move an object up, move an object down, left or right. Those are going to be your arrow keys. Menu options, there's all F function keys, F1, F2 or something. So rarely are you actually typing something in when you're using a graphics program. You can also check one of the modifiers, for example, the shift, the control, the alternate. So if it's depressed, you're going to get the, and they're called modifiers because they're not inputting anything, they're giving you modifications on the input. It's a control F instead of a control, instead of an alternate F. Or it's a combination that you're looking for. Also emulated on a 3-button mouse with a 1 or a 2-button mouse as well. So in terms of reshaping the window, you can reshape and resize the OpenGL window by pulling the corner of the window. Obviously, what happens to the display? It must redraw the application. Might be two possibilities. Display part of the world, display the whole world, but force it to fit into the new window. So you can alternate the aspect ratios. Something, a lot of flexibility actually. Here's an example of the reshape. The reason why these functions are in here is because this does not happen automatically. When you create something in Visual Basic, something in C, you're using my Visual Studio as an example, and you create a window, and inside of the window you have all the Microsoft, in this particular example, all of the Microsoft built-in functionality that's doing this for you. If you're not using that, you're using OpenGL, you got regular old C. This is not the MFC library. This is a window that's drawn by OpenGL. Objects that are placed on the window, and so you're going to end up with this kind of an example. Here's the original, we resized it. So on this type of an event that occurs, you're going to have to tell the window what to do. And this might be, well, move it up, make it smaller, make it bigger, resize it, or just cut it off. What if you don't want to resize it? You don't have to. So you might, argue and say, although this has to be done manually, not going to happen for you automatically, that you have more flexibility, because in like a Windows program, you can't do this and move the window up and get rid of something that's in the window. No, the whole thing's going to get smaller on you, usually. The reshape callback is called automatically as the event of the reshaping of the window. So the glet reshape is going to do, as an example, my reshape. This is just an example of what the information you'd put into the callback function. So it returns the height and the width of the new window in pixels. So a re-display is going to be posted automatically at the end of the execution of the callback. And Glut has a different Reshape callback, but probably want to define your own, actually. Otherwise, you're going to have unpredictable behavior. If you use the default information, you're probably going to end up in a situation where you're going to have enough control. So the more callbacks you put in, the more control you have over the environment and what's happening. So the Reshape callback is a good place to put viewing functions because it's going to be invoked when the window's first open, perhaps. Exit functions, clean up any memory. So in terms of the example Reshape, this Reshape example is going to preserves the shapes by making a viewpoint of the world that's smaller. Same aspect ratio, but it's going to be smaller when you've resized the window. And so instead of making those objects go out of view, you're just essentially changing the aspect ratio. And here's what it's doing here: switching the matrix mode to something. So we've got the projection going on. We're going to load the identity. We're going to actually put the object in. We're going to call essentially and create essentially a smaller version by resizing it by the distance for which the window is moved or reshaped by. So, toolkits and widgets, more stuff. So we don't have built-in menus, widgets, tools, and things, but we can do it. And just as a caveat here, although these facilities exist, I don't think I would create a Windows application using any of this stuff. If I were going to create if I wanted to create a notepad or something, or a Windows application that was not graphic intense, I wouldn't be using the graphics libraries to do this. Instead, I would take and create, let's say, a Microsoft Visual C++, Visual Studio, MFC interface. And then for the graphic portion alone, I would use the OpenGL or the Glut library, which is supported inside of that development environment, just like it's supported in Dev C++. But if you wanted to do it in Glut, the facility actually exists. Kind of primitive, so most Windows systems have toolkits or libraries or functions for building user interfaces such as Windows. They're also called widgets. So widgets are sets that include tools such as menus, sidebars, dials, input boxes, and it's actually called a widget. Well, it's called a widget computer graphics. I think we would call them Canvas. I think that's what it's called normally in some Microsoft Foundation class and different types of Windows type of programming environments. But toolkits tend to be platform dependent. So as I mentioned before, you're probably going to use the toolkit for the platform that you're on. Like, for example, I keep saying MFC, but I'm not sure you guys even know what I'm talking about when I say that. But MFC stands for Microsoft Foundation classes. So it's integrated into the Visual Studio. So when you create a window, the window looks like a Microsoft window automatically for you, because it's using the foundation classes or the object components right from the operating system. You're calling and making instances of the window object. Same window that shows up when you open up the control panel or when you open up the Explorer. It's all essentially the same object, and you're being able to call it from an API inside of your program. So it definitely gives you a lot more flexibility when you're using the underlying operating system motif. So your program looks like it came from that operating system. You can tell the biggest difference when you look at Java programs. They're not using MFC. A Java Windows program is going to look like a Java program. It's using Abstract Window Toolkit, or it's not using MFC. So the windows don't look like Microsoft. Believe it or not, there's third-party tools out there that actually take the Java and convert it to MFC. So your Java program can look like a Windows program. But the interesting thing is if you leave the AWT or you leave the Java components in their swing components, you get some cross-platform compatibility, so your application actually looks the same on a Windows machine versus a Mac versus something else, which is one of the benefits you have, because you can't accomplish that with an MFC library. You can only use that on Windows. So in terms of OpenGL, you've got the same kind of choices. If you use the OpenGL, you're looking at a more cross-platform, but you're looking at a less operating system specific implementation. Or you use Glut, it's going to provide the widgets including the menus and the basic toolkit for the underlying platform. So it's going to create something that looks like a Windows motif, or looks like a Apple window of some sort, or OS X window. So for menus, Glit supports pop-up menus, and that's a menu. Can also have sub-menus. So we have 3 steps to create the menu. We define the entries for the menu, we define the actions for each one of the menu items, and then the actions are carried out if the entry is selected. And then we attach the menus to the mouse button. So the menus occur when mouse buttons are clicked and things of that nature. So here's defining a simple menu. It's a little simple example. In fact, I have another menu, I believe it's called menu.c out in my examples directory. And you'll see a ton of these actually online. And menus are actually, they look complicated, but they're really easy to put together. Here's the menu. It's going to have a clear screen. It's going to have an exit on it. And so we create the menu, my menu, which is going to be the object that we're going to send to it. It's going to create it. I might have a clear screen. That's going to be number 1. Exit, which is item number 2. And then we're going to attach an event. It's going to be the right mouse button. So when we click the right mouse button, something's going to happen when we click that on the menu. Kind of primitive if you think about it. If you've ever done any Windows programming at all with Visual Studio, this is kind of archaic a little bit, because now we have GUI tools. We just drag stuff on. I can't, oh, let's create it in a window. We have these tools that are built and it creates it for us. But if you think of the concept, we have a little less control when we do it that way. This has got a little bit more control to it actually, in terms of, is it the right mouse button that clicked it, or is it the left mouse button that clicked the menu item? You know, so we can put a context-sensitive help in or something, or change the behavior. So we're in more control of the behavior. Entries that appear in the right button when it's depressed, identifiers in terms of the buttons themselves. And then we have the menu actions, and here it is. Here's the menu callback, where we have, if it's 1, clear the screen. If it's 2, exit. So we get those 2 components from the function calls, essentially, that we've defined the identifier as 1 or 2. So it's essentially going through a bunch of, you know, if it's this, do this. If it's that, do that. And we put functions over here to say, you know, run the exit, run the this, run the that. So note that each menu has an identifier that's returned when it is created, and we add sub-menus to it. And here's a way of doing a sub-menu actually. The entry, this one is a parent, this one's a sub. So we give the sub an ID to say, this is sub number 1 of parent. This is sub number 2. And parent's the highest level, so we're not going to have more than, we might have more than 1 item. Parent 1, parent 2, parent 3. And we have sub-items that are put in each one of them. That's how we create, as an example, the file menu, the view menu, the tools menu. And then underneath file, we have open, new, close. And underneath view, we have minimum, maximum, or whatever options that we might have available. So, some other functions in Glut that we can use: the dynamic windows, creating and destroying during the execution, save a little bit of memory if you wanted to. Sub windows, so we can have we can create a full-fledged application out of this. Multiple windows. Changing the callback during the execution. Timers, maybe some portable fonts. Using font systems from underlying libraries, bit characters, stroke characters, all sorts of different things. So, kind of quick, but that was part 2 of the lecture number 8, tonight's agenda. Last but not least, and don't worry, I'll go through it just as fast, is another one going through some better interactive programs. You've actually, believe it or not, seen a really good overview so far of all the callback information for the mouse and the keyboard, all of the event-driven stuff, and it's really just kind of simple. What this lecture does is it gives you kind of more advanced options that you can do to apply the basic concepts, but then look at it from a little bit more of a sophisticated kind of graphic interaction point of view. Learn to build more sophisticated interactive programs using picking, where we can select objects from the display. We have 3 different methods for picking, actually, that we're going to take a look at. And picking is when we, you know, it's not clicking, but you can kind of think of it the same way. We can pick an item. We have the objects. When we click an item, it's more like, you know, this is the XYZ location. This is the coordinate of where the mouse clicked. When we pick, we say, this is the sky, this is the beach. This is the lamp. So we can pick the lamp as an object and then have the object do something. Come into view, go away from view, go away, disappear completely, do all sorts of different animation with it. We have rubber banding. So that's interactive drawing of lines and rectangles that all work together. And then the display list, retained mode graphics. I'm going to talk about that a little bit in this lecture as well. So, picking. Identify a user-defined object on the display. Pick the lamp, pick the couch, pick the chair. So the entire object is the location, not the XYZ coordinate. So in principle, it should be as simple because the mouse gives the position, and then we should be able to determine which object is at that position. What does it correspond to? If we have objects that are overlaying other objects, it's hard to pick. So we have difficulties. So practical difficulties. Pipeline architecture is free forward, hard to go back, screen back to the world. As I mentioned before, it's hard to go backwards through the picking. Complicated. By screen being 2D world is a 3D world. We're picking on a 2D world in a 3D world scene. So the picking mode is different than the graphic mode, which is kind of interesting. And how close do we come to the object to say we have actually selected it? So it's kind of like what we have to do when we do this with images, image maps, and things like that, like in HTML programs. We define the coordinates, and you're just next to it. You don't want the user to be clicking all over the place until the thing highlights. You want to make it. You might stretch the object out a little bit, around it a little bit, so you can essentially create an easier pick. So which means your objects aren't going to be as close together. So there's three approaches to accomplishing this. You can have a hit list. So most general approach, but most difficult to implement. We have a list, and we have coordinates that are associated with it, and we have we keep track of it. So use back or some other form of buffering to store the object IDs as objects are rendered. If we have a hit list, then it can go through the list and say, well, at this coordinate system, this is behind this, which is behind this, which is behind this, and they're all at this particular location, and then have one by default actually be the one that's going to be picked, maybe. Or rectangular maps, so easy to implement for many different applications. See the paint program and the text. Well, that's going to be in the red book, if you're familiar with that book that I pointed out a couple weeks ago. There's an excellent example of a rectangular map. Or just go onto one of those example sites and put in rectangular map. That's what I was talking before. If you're familiar with HTML program, there's this thing called an image map. It's a rectangular map that you've created where you've set, from this coordinate to that coordinate. Everything in between is part of the pick, essentially. So rendering modes. OpenGL can render in one of three different modes. So we selected by the render mode, and we've given it the mode that we want. Well, we got the GL render, which is the basic mode. If we leave it out, it's going to be by default. So normal rendering to the frame buffer is the default. We have the feedback mode that provides a list of primitive renders, but no output to the frame buffer. So we've got the list that we can do a hit list with. Or the selection. So each primitive in the view volume generates a hit list that is placed in the name stack, which can be examined later. It gives us more information, creates the list for us, makes it so that we can select objects for potential pick items. So selection mode functions look like this. Obviously, you're not going to learn this stuff by looking at a slide with a bunch of names of functions on it, but hopefully when you start implementing this, you'll be able to identify at least or have some familiarity with what some of the mode functions might be. Popping an item onto it's a stack implementation, so we can select the buffer, selects the name buffer, initialize the name buffer, push an item on it, pop an item off of it, load the name, replace the top name on the buffer with another one. These would be items that are going to be in the hit list that are going to be stored in the buffer given the mode that you've selected. So the ID is a set of application programs to identify the objects, kind of like the menu IDs actually. So using the selection mode, so we initialize the name buffer, enter the selection mode using the mouse, have to have some activity that occurs with the mouse to get into this. We've clicked somewhere. Rendered the scene with the user-defined identifiers. Enter normal rendering mode. Operation returns a number of hits. Now we got the list. Examine the contents of the name buffer, the hit records. Go through the list. Hit records include the ID and the depth path and information, and then figure out which item you want to select. You can actually pick an item in there and say, you know, this is the top item, this is the next item, this is the next item. You may also use, as an example, key combinations along with the mouse to perform this. So selection mode and picking, as we described it, selection mode won't work for picking because every primitive in the view volume will generate a hit, if you think about it. As I mentioned before, or I just mentioned 2 minutes ago, 2 seconds ago, hard to do unless you're identifying. You know, how do you know which item is actually going to be identified in this hit list? You know, you've got 5 different options, and you have one to choose from. So unless you hit a default or make maybe a combination of keyboard hits along with the mouse event to actually select the item, and it makes it kind of difficult as a user interface. There's no program out there that requires you to click on something and then press a key to tell it, say, which one do we want that we just clicked on? That doesn't really happen. We can change the viewing parameters so that only those primitives near the cursor are in the alternative view volume, and then we can do a pick matrix. So we'll also have an example of that in the red book as well. So using regions on the screen, we get this actually when, this looks like Java programming to me actually. Many applications use a simple rectangle arrangement of the screen where we have the top version, toolbars, maybe some drawing area, some menu items, or we can flip it around, put the menu items over here. So easier to look at the mouse pointer positions to determine which area of the screen when using a selection mode picking. So if it's over here in the menu, we don't have as many items to pick from, so we can essentially dissect out the regions of the screen, make the regions of the screen more reactive to the mouse clicks and to events that might occur. So using another buffer as an example, and colors for picking. It's kind of interesting. So for a small number of objects, we can assign unique colors, often a color index mode, to each one of the objects. Then when it's rendered on the screen, if the color buffer to the color buffer other than the front buffer, so the result of the rendering is not visible. So we can then use the mouse and use the read pixels to read the color of the buffer that we just wrote at the position of the mouse, and depending upon what what color is stored in the buffer, we know which object was actually visible to the user, and that was the object that was actually clicked. So it keeps track of it by color combinations. Returns to color gives the ID of the object. Because at any one moment of time, the object might not actually be there. So if you've got multiple objects that are stacked on top of each other in the same plane, and some of them are visible and some of them aren't visible, you pick it up. So it's easier to click on something. So here's writing modes. So the application out here has got a source. Source comes in, bitwise logical operation kind of occurs with it, and then we write the pixel to the destination, to the frame buffer. Then we go back up and we read another pixel, write it, read another. So this is essentially a kind of a, looks like kind of a complicated diagram for what it's really describing, but it's essentially taking in and reading, not really queued, but more of a real-time kind of cycle that happens in terms of the source of the information and the writing the pixels to the frame buffer. We can also do an XOR write, and this would be writing it to a frame buffer. The XOR write also uses the default mode. If you don't place it, you're going to get this automatically. Source replaces the destination automatically. Can't write temporary lines this way because you can't recover what was underneath the line in a fast, simple way. It's not double buffered, it's simple. So exclusive OR mode perhaps can also be used. So the mode is to write a line. We can draw it a second time. The line is erased. First line is erased actually. So now we have rubber banding as a concept. So we can switch to the XOR mode, write mode. So the read-write mode, read only, execute only. The drawing in the object for the line can use a first mouse click to fix one of the endpoints, and then use the motion of the callback to continuously update the second endpoint. And this is in terms of describing the rubber banding technique. So each mouse is moved, redrawing the line, which erases it and then draws a line from the fixed first position to the second position. So at the end, the switch back to the normal drawing mode is done and you draw the line. So it works with objects, rectangles, and circles. This is, we take this for granted, but if you go into Microsoft Paint, this is rubber banding actually. You click, let's say you click an object to draw a square, you click on the canvas, you hold the mouse button down, you drag it out, and you get a square of the size that you've dragged it to. That's rubber banding. So we can implement that as a concept in our OpenGL program in terms of drawing a line. The initial display might look like this. We draw a line with a mouse. So we start here, we end here of the second position. We can move the mouse into a new position, draw a new line. The original line might be redrawn, so the new line can also be moved. We can put multiple lines in there. We can essentially, this is in terms of rubber banding lines. A little bit more complicated to rubber band more objects, but it's done the same way. So. In terms of the OpenGL XOR support, there are 16 possible logical operations between the two bits. They're supported by OpenGL, so the first enable logical operators, a color logic operator. You can choose logical other operators if you want, copy operators, some of the other stuff. So intermediate and retained modes as well. We're calling this standard library. Once the object is rendered, there's no memory of it. And it can't be redisplayed, so we must re-execute the code for it. Well, that's one of the interesting things, actually, in terms of retaining. You have to buffer it. If you don't buffer it, you lose it, which is why some of that stuff gets half painted in a single buffer mode. So we have a concept known as intermediate mode graphics. So essentially, slow if the objects are complex, but must be sent over a network. It's because you're saving the information so you can redraw it. It's alternative to defining objects and then keeping them, some of them from the redisplay. So it makes them redisplay easier. Retains the mode graphics accomplished in terms of the display lists, if we correct it. So a display listing concept is conceptually similar to a graphic file. Must define a name, create it, add contents to it, and close it. So imagine what you're doing essentially is keeping information. You're tracking the draw, you're tracking display information so that you can redraw it. And so you have memory when there's no memory. So if you use the display list, you're essentially saving it in a temporary buffer. So in a client-server environment, display list is placed on the server so that when the client reconnects, it can just open it up, look at it, read it, and redisplay it. So it can redisplay without sending primitives over the network each time. Because a network connection is for graphics, it's going to slow everything down anyway. So, but if you're working on an internet-developed application and it's using OpenGL, you're going to be reading something from a client to a server. And you might not necessarily want to be keeping track of all this graphic stuff. It's going to slow everything down. So creating a display list here, we can have the ID, have an integer, ID is going to be equal to the display list. Create a new display list. We open up, we end the list. We call a create list, create the list, and then we open it up, and then we save it in there. So OpenGL functions can be put in the display list. State changes may also be inside a display list. So avoid unexpected results by using the push attribute, the push matrix, upon entering the display mode, hopefully. And then the push attribute and the pop matrix before exiting. So we can essentially run them in a kind of a good essential order that makes sense. So here's an example using a hierarchy and a display list. So consider a model car. Here's our little car. Create a display list for the chassis, create a display list for the wheels. If we have a display list, we're going to keep track of all the different components that are associated with this object in terms of how they're going to be drawn and what order they're going to be drawn in. Here's a new list where we have the chassis and we have the wheels, and we keep track of all this information in the list, and then we can essentially, maybe I should have left that up there for a few minutes because I wasn't done talking about it, but we can essentially call it when we want to or have to redraw, let's say for example, the bottom of the car, or the top of the car, or the sides of the car, or something. Okay, that was 3 quick lectures on everything interactive having to do with OpenGL. Next week I'm going to have some examples I'm going to show you was going to get back to that card that was at the end. Oops. The card's not going to show. Hopefully my program's not going to bomb out either. Okay, good. In any case, next week I'll have some examples that I'm going to show you that's going to put all the pieces together rather than going over the concepts. We'll look at the OpenGL part of it. And then next week I'm also going to introduce some more concepts. We still have shading, lighting, and color as some important concepts to go over as well. So, questions, comments, or concerns about the course, anything that's going on? You guys got the midterm last time? Let's take a look here. If you haven't found it, I put the midterm out. 991, let's see. It's due on December 12th, and December 12th will also be the same day as the final exam. And I believe the LMS is now populated. However, some of the assignments cannot be uploaded yet. So if you're struggling to get the work done, just keep the work on your local computer, and then within about a couple weeks, hopefully before December, I would hope, system should be ready for you to upload stuff. So unless we have anything else, any questions or anything? If not, we're done for today. All right. Well, thank you all for coming.